Welcome to this year's BAA solar section meeting, which we're holding as a webinar. The webinar is being broadcast on Zoom and also got a live stream to YouTube. And after the meeting, you'll be able to watch a recording on the BAA YouTube channel. As usual, you can ask questions by typing them into the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end of each of the presentations. It's my pleasure to now hand over to David Arditti, the President of the BAA.
Hello, thank you very much, or wherever you are, for joining our webinar. So I'm the President, and on the programme it says opening address, BAA President, rather grandly. So I won't take up much of your time. I will just say, well, thank you very much to Lynn, Director of the Solar Section, for organising this, and to Andrew Wilson, who's our technical expert. So we started doing Zoom meetings and Zoom webinars during the lockdown, obviously, and we've continued with them as a policy decision. We've decided, as well as doing our normal meetings where we actually meet in various locations around the UK, we carry on doing webinars because we found they're an excellent way of us keeping in touch, particularly with our international members. So some of the section meetings now have gone back to being real meetings, such as the Deep Sky meeting on the 19th of March will be a real meeting, but it's up to each section what they want to do. And the solar section has decided to hold a webinar. And another thing we decided was that we would make it open to anybody, whether they're a BAA member or not. And wherever they are in the world, you're very welcome to join in and ask questions on the in the chat box. If you're interested in observing the sun, then you're very welcome. And if you like what you hear, you might consider joining the BAA. And we have various membership packages, which you can read about on the web. Many of our international members go for the digital subscription because then that's cheaper. We don't have the expense of sending you out the printed documents. You get our journal and our handbook digitally. So the solar section has always been one of the busiest and most active sections. I suppose that's because the sun is always active, nearly always anyway. It's the most dynamic object in our sky, the most obviously dynamic, and it's a thing which is relatively easy to observe and easy to contribute to the science to and our knowledge to and our records of, using relatively inexpensive equipment. Yes, you can use expensive equipment if you want, but we've got a talk later on about imaging with a low-cost solar telescope, so we'll find out actually how that works and how low cost it really is. But you can, with relatively simple equipment, you can contribute to knowledge about the activities on the sun and contribute to our long records of solar activity, which go back over a century in the BAA. So, without further ado, I'll present to you our Solar Section Director, Lynn Smith.
Thank you, David. I'll just share my screen, hopefully. Right. Right, well, welcome to the Solar Section webinar. It's the first time we've held one for a couple of years. It's a fantastic time to be holding it because the sun is now starting to get rather active as we move up towards solar maximum in the next few years. We've had sort of a quiet lull, and then of course December and January brought us a huge upsurge in solar activity. Decreased again towards the end of January, but in February, although it started sort of quiet, it started getting into gear once more. And in fact, we recorded the relative sunspot number R as over 200 on the 11th and the 14th for the first time in this solar cycle. So let's have a look then at the solar activity of recent days, the last sort of 10 days or so. So on the 7th of February, we had 3 sunspot groups, which had sort of newly come onto the disk. But on that day also, Pete Lawrence managed to get this rather stunning prominence captured on the eastern limb, again, just in the early afternoon on the 7th. And no matter how many times you study the sun and for how long, it still amazes me to see a prominence like that, and then Peter's very kindly just put in the scale of the Earth there, and it's still sort of quite astounding, really, to see your own planet up against a feature like that on the sun. Amazing. I think we have a second one from Pete there showing a slightly sort of different orientation of that same feature. Following day, we didn't have an awful lot of difference, but this sunspot group up here, 213, has to start to mature, and indeed continued to do so. Very nice image here of it from Carl Boron, showing it in H alpha. They've got a nice filament down here and some arch filaments along there, which are just sort of connecting the two areas of polarity, stabilizing the sunspot. And we can see here we've got some sort of bright plage and even some minor flaring going on too. Following day, on the 9th, you can see up here 213 is starting to mature, starting to extend in longitude. And then we have the first appearance of 217, soon to be followed by 220 around the eastern limb. Carl Boron gives us a very nice calcium K-line image of what was going on that day. And it's not just the plage that we can see around the main sunspot areas, which we can perhaps expect to see, but it's the extent of the plage over this area where there aren't any sunspots that is quite fascinating. I think Brian Mitchell from our section comments quite a lot on the calcium plage, and that's a nice example of calcium plage across the disk not being associated with sunspot groups. Also on that day, on the 9th, we have Roger Samworth, who spotted this fantastic prominence, eruptive prominence, over the space of about an hour or so. And then you can see this little nodule just starts here, 821. And then half an hour later, it's blended into this fantastic eruptive prominence. And then Roger follows the sequence straight through for another half an hour until it's lifted from the disk and disappeared altogether. And that's something I think Peter Meadows will be talking to you about later when we start talking more about projects for the section to do. So on to the following day, 10th. Again, we can see that 213 is extended in longitude, so it gets longer and longer as it goes on, and 3220 has now appeared around. So these two sunspots, particularly this one, showed some promise at this stage of development, but sadly it kind of got a bit disappointing. And so they are both just now a pair of penumbral sunspots just traveling along the disk quite boringly on their own. So here I can see even more extension by this one, probably an F-type group by this stage. And this one, again, showing some promise, particularly sort of extended areas here. You think, well, that's going to mature nicely, but it failed to do so, really. McNichols produced this nice H-alpha image of those sunspots, 217 and 220. And you can see the whole area between them is just flaring and full of nice filaments. So nice image. Following day, again, we're losing this one now. It's disappearing off towards the northwest limb, and not a lot of progress with the others. I've arrowed this. You can see here nothing in particular, but the following day, just overnight, we have 3226 as developed as a nice mature sunspot in just a matter of a few hours. Stuart Green, he captured 3 very nice images of the disk on that day. So here we can see the new group and our favorites here. But my favorite one is this one in H alpha that he produced. In a white light, it doesn't look too spectacular, something going on, but not a huge amount. But I think it's this H alpha image here that really shows you what's happening in the disk. It really shows you all the fantastic activity with the plage and the filaments, and even this very nice hedgerow prominence down here. You can see that's our newly developed sunspot that's just come onto the disk, or developed on the disk rather, and you can see how bright it is in H alpha plage. And even the old sunspot disappearing, it's still quite bright as well. And this whole region between 217 and 220 is quite spectacular, and amazing associated filaments too, and quite a few sort of around about. So absolutely stunning image. Same day, same time, more or less, in calcium K-line also gives us the calcium plage effect too. Following day on the 14th, that new sunspot is matured quite nicely, and these two are settling down to what they did become, which is just two single penumbral sunspots going across the disk. And we have Jared Corchi here captured that entire area, again showing the camouflage, and also this this wee one here that just have snuck in. And Arthur Coombs from Australia sent me this in for the 13th and 14th, and this is 217 and 220, and it's got this rather nice filament around it, but this lovely filament here, which is like a sort of an eyelash really over the eye and the eyebrow, which made quite a stunning image. Sadly, the following day, the eyelash had moved on, and we lost the effect. 15th of February, not a great deal of change. Nichols sent in this nice H-alpha image of the main three groups in the eastern sector. So you can see there's plenty going on with plage and nice filaments. And also we have some flaring going on from that main sunspot that's just developed, 226, and this is by Carl Boron. So it's quite interesting there. I don't know what's happening there. Something seems to be intruding there into the region of that sunspot. Carl also sent me this, which I thought was worthy of note as well, how we can get a prominence, and this shows sort of development over quite a short time. It's only 12 minutes. It's all to do with luck, of course. You just happen to be observing when these things, crack off. But here we have this nice prominence, and we can see that we have some development here and further development, just in the case of 12 minutes, just following the development of that particular prominence, which is quite a nice sequence. So the 16th of February, again, not a huge amount of difference there. We're just sort of plodding along quite happily with this sort of large area, really, where nothing's going on. But yesterday, we got a new area coming around, 3229. And this morning, that was really quite bright. And go on here, that was quite bright in plage. If I just go back, you can see this one, 3225, which wasn't doing much. It just started strengthening yesterday. And then today, it really has started to mature. Bit of a shame because it's about to track off. But that was bright in plage this morning as well. And in fact, there was a subflare at just before 10 o'clock UT this morning. I was observing just after it, so I'm just sort of catching the cool down period from it. So we've also caught this one here just coming around. So probably it'll be 3230 when it gets around to being numbered. So hopefully we've got some more activity coming around the Eastern Hemisphere to sort of fill in this big void that seems to have developed in the track of our Western Hemisphere activity. Right, just moving on, you will be aware that the BAA has a Twitter account, and that's what it looks like. The president has very kindly allowed the section directors to have access to it. And so from about last December or thereabouts, I've been putting on some solar images that you've been sending into the section for archiving. So please carry on sending in your images, drawings, sketches, anything at all, and I will from time to time be putting them on our Twitter account. So there's a few of the images that I posted, I think, back in December, but quite a few more have been put on since. Obviously, I do have to bear in mind it's the BAA account and not the solar section account, so I have to be kind of a bit diplomatic. But let us just say the solar section is very well represented on the account. So do keep a lookout on Twitter and see your images, hopefully getting plugged on there. Now, moving back to October last year, we had a partial eclipse, and from the UK anyway. And we have here a very nice sequence by Nichols in calcium K-line showing us that eclipse going on. There's quite a few of you are out there doing your thing, and this is also a very nice sequence by Carl Boron and Roger Samworth showing the H-alpha view. And Pete Lawrence was also busy at work, and Simon Brown too, as was Ella Bryant, capturing some very nice prominences there, which makes quite a stunning photograph. And Stuart Green showing us the calcium K-line image. And Philip Torsey, who must live halfway up a mountain somewhere in the Pyrenees, I think, because his seeing is always fantastic clarity, absolutely beautiful. It's always worth keeping an eye on Philip's account, his Facebook account, having a quick look at the pictures that he posts on there. Has plenty of stunning astronomical images, quite a lot of solar stuff, and even some very nice birds of prey as well, if you're interested in that. Richard McKim sent me this in, quite a complex diagram of the partial and full literature around it. And I'm very pleased he did. I get so few of these now, and just about everybody's into imaging and very, very few sketches. So I do keep plugging. If you're at all into diagrams or sketching or anything like that, please do send your work in for archiving. I'm very, very pleased to receive this kind of work. It's becoming rarer and rarer. You're probably quite familiar with the work of Mr. Druckmüller. That's quite a famous total eclipse picture from a few years back. And the reason that I'm mentioning that is because he has his website. And if you go onto that and you click down to Solar Dynamics Observatory videos and images, it gives us a bit of a lesson on how to produce the kind of images that he does. He takes the SDO images and he has his algorithm and then he works at it and he teases out all the fantastic detail to make some very, very dramatic images, which I'll show you in a moment. It does say this is not an easy task. So probably not for beginner, but if you're an old hand at imaging and you're a bit bored over the winter or whatever, and you want a project, or just like a challenge perhaps, then have a look and have a go if you want and see if you can produce something like the images he does. So, I mean, they're just absolutely stunning effects that he produces. Amazing. They're even just worth having a look at if you don't want to have a go. He's got quite a few on there. I think you agree. It has quite an effect. It just teases out all the detail and makes the sun look the most dramatic object for observation, which of course it is. But it really enhances what's going on there. Incredible. And there's some post-flare loops just to end with. Right, I'd just like to spend a few moments going over the Q factor. Of all the observations I get in, there's relatively few people report on the quality number or Q number. So I'd just like to very quickly run through how you can report on that. You'll see on my reports, on the monthly reports, I refer to most sunspot groups with 3 letters. The first letter is the only one that we concern ourselves with for the quality number. So forget the other 2. If you want to read up about that, there's a full article on the solar section web pages about the Q factor, and you can read all about it on there. So it's just a matter then of doing your observation, and once you've finished, then assigning every sunspot group that you've recorded with a letter which designates the type of group it is. So you make your decision as best as you can. So the smaller the group is, obviously the smaller that the number value attached to that letter is. So A is a value of 1, B 2, C 3, 4, 5, 6. And then we have this solo penumbral sunspot down here, which is an H, and that's given the same value as a C group. So it's a value of 3. So what does that mean in reality? Well, if we have a look on the solar disk, and let's just have a look at a few examples. So here we can see we've got, if you've got really good eyesight, anyway, you can see there's 2 very small spots there, little pores. Neither has a penumbra, and they're in a very small area of maybe 1 or 2 degrees. So that is designated as A. So that's the least sunspot. So a small pore traveling on its own would be A and given a value of 1. Here we can see we've got a more of a cluster of sunspots. Again, nothing has a penumbra around it. And that is a B class and given a value of 2. Over here, probably not the very best of examples because it's not particularly big, but you'd have to take it from me that does have a small rudimentary penumbra around it. And we also have a follower. So we have a penumbral spot, or one with a rudimentary penumbra. If you can see any sort of penumbra at all, then that's good enough. And then usually 1 or 2 followers with a tiny one just there. Makes that into a C-type group and given a value of C. And then we have down here on the limb somewhere, yeah, we have this one. So it's quite substantial. So that is a D-class group. So it doesn't exceed 10 degrees in longitude, but it's got at least 2 penumbral spots, leader and a follower. And here we can see probably got 2 followers there. So that's a D class and gives us 4. And this one down here, much smaller, but it's actually the same. It's still a D class. They've both got penumbra, one following the other or thereabouts. So it's again less than 10 degrees in longitude, so a D class group. So on here we see an example of the larger ones. This will exceed 10 degrees in longitude, but not 15, and therefore it's an E class and given a value of 5. And then here we can see it's quite a long group there. It's an F-class group, exceeds 15 degrees in longitude. And again, we've got our penumbral spots following and leading. So it's an F-type group. And that gives us a value of 6. So that's all you have to do. You don't even have to divide it all up at the end of the month, because if you go online, you just fill in the columns like you do with everything else. You decide, once you've decided all your groups, A through to F, you've assigned your numbers, you just add those numbers up and you just put them in the Q column. And at the end of the month, click on the boxes and it will work out the MDF for you. And then you can report in Q. So it's very simple, it's very easy to do. And it's just really a matter of practice to work out which groups are what. Right, I hope many more of you will start reporting in Q, because that'd be great if you did. Peter and I have been discussing about some projects, and Peter is going to certainly discuss that in more detail than I am. So we'd like to sort of launch 1 or 2 imaging projects with you today. And that's either images or drawings, and it's just to sort of add a bit of interest and focus people down onto your observing, rather than just sort of regularly doing sort of boring all the observing, just to sort of do something a little bit different, provide a bit of a challenge. You don't have to take it up, of course, it's just for those that might want to do so. But little focus observations, provide us a bit of a challenge, and also give us something for the archive, a little bit out of the ordinary. So I'd like to talk just for a second or two about white light flares. Probably fairly rare sort of things, but maybe not quite as rare as we think they are, especially with all the kind of equipment that we have at our fingertips these days. Especially as we're going up towards solar maximum, it's a good time really to sort of trying to bear that in mind as search for white light flares, because they're certainly more likely to be happening in the next few years than they have in the last few. Now, what are they? Well, the very intense releases of energy are visible in the photosphere as a white light feature. So it's an energy release in the corona is so intense that it's able to penetrate into the lower chromosphere and through into the middle photosphere. Now, they are quite, in white light, short-lived events, maybe only just a few minutes. So again, we're down to sort of good luck in just having to be in the right place at the right time, or imaging at the right time. But it's certainly worth a look. I mean, if you're imaging in H-alpha and white light at the same sort of time, don't forget, check your white light image over for any flares that you might have recorded in HA. You never know. Famously, Richard Carrington, of course, saw the white light flare in 1859 and made that drawing of it. So that's the kind of group we should be looking out for. And if you think, well, I don't think we get many of those, we got one at the last solar maximum, which famously was this one. So if you're looking out for something like that, you know, you can almost imagine the complex magnetic fields surrounding that spot. It is such a mess. And if I go on to this one, that was at the previous maximum back in 2003. And again, you see a fantastic similarity in the sort of the construct of those spots. Interestingly enough as well, look at the dates. I mean, 2003, that was a fantastic image from an amateur. And then just 10 years, 11 years later, look at the difference in equipment and expertise and skills. It just goes to show how imaging has come on over the years. But anyway, I sidetrack a bit. Going back even further, 1989, some of you will remember, of course, the huge sunspot that caused the electricity grid to black out in Quebec. So again, you can see from the sort of construct of that spot, we're dealing with a very similar kind of thing. So that's certainly something to look out for. If you see a spot like that coming on the disk, then it's a matter of observing it all day, every day, I would suggest, as much as you can anyway. But it's not always those really big and complex spots that will release a white light flare. This one back in March was certainly not that kind of group, not quite that big, but it did release a white light flare. Sadly, this isn't it. It was flaring at this moment in time and on that day, but that's the only image I've got of it in H-alpha. That's what it looked like in white light. So not as spectacular as the ones we've just seen, but as you can see there, it is pretty messy. We've got a lot of sort of the asymmetric penumbra around all here, and even this sort of messy bit here. So it doesn't look like a sort of nice, stable, ordinary sunspot. So again, look out for something a bit messy. You never know, you might well just get something. And this one was in March last year, just about 12 months ago. You can see it flaring here. It wasn't really that messy, but again, it wasn't the sort of normal leader-follower construct either. So look out for something like that. I think that only produced M-class flare, if I'm right in thinking, but it did produce a white light flare. So even some M-class flares will produce white light flares if they're intense enough. It doesn't have to be an X-class flare, which is quite interesting. And Kennedy, I think, captured a lovely picture of it there. So you can see it is pretty messy. So that is the kind of thing to look for, something that isn't a conventional spot, and just keep your eye on that. Image it as much as possible and just see what you've got. David Test produced a nice image of it there in H alpha. And here we have Stuart Green produced this one in the K calcium, showing the K calcium plage, and again a white light one of it there. And that's it. So I hope that you will look out for white light flares, and I hope that you'll also do the Q factor for me as well. So thank you for listening. And if you've got any questions before I hand over to Peter, I'll be happy to answer them.
Hi, Lynn. We've had a couple of questions, which I think Peter is answering in the Q&A.
Brilliant.
If you want, I can read them out in case they're of interest to other people as well.
Yeah.
Which is an anonymous attendee asked, what is the comments box used for in the WL database? And Peter's answered that it can be used to add if you have observed any protected naked eye sunspots, for example, or if you noticed something unusual. We've also had a question, which is again from anonymous attendee. How do you assess a spot group that is moving around the limb with only, say, one spot with penumbra visible?
Yeah, you can only assess it by what you see at that moment in time. So you don't assume what's gone around the limb or what may come around the limb if it's eastern. You just assess it on what you can see. So if you only see one small penumbral spot, for example, it would be H-class group.
And we also have Michael Nichols asking, with the solar activity increasing before it should, is this an indication that this cycle will be shorter than 11 years?
Well, who knows? I mean, that is the answer to that one. Even the experts can't tell us. I mean, famously, they make predictions which always turn out to be wrong anyway. So they've no idea. I mean, they did say this wouldn't be a particularly active cycle. It's turning out at the moment to be so, but we don't know how it will mature. So I mean, that is the strength of the section. You know, we don't predict what's going to happen. We just observe, and then, you know, in time, we will tell you what did happen. And that's where I like to be with it. I'm not in the business of predicting. So, Mick, I don't know. Perhaps you do.
And then we have Simon Brown has asked, there's no mention of last night's X2.2 flare, the largest of this cycle. This could hit Earth even though it came off AR 3229?
Yeah, I think I'll leave that for Peter because he was mentioning it to me quite earlier. I missed that one, but Peter, I think, did either observe it or knows about it. So I'll leave Peter to answer that in the next session. Yes,
is there anything you'd like to say now, Peter?
Yes, I can do. No, I just saw actually on Twitter that there was an X2 flare yesterday evening, I believe it was, which so it's the first X2 flare of this cycle. So that's quite exciting news and a good indication of how the cycle's going.
Great. And so I think that covers all. So that's all the Q&As. There's nothing which has come through on Zoom. So, Lynn, shall we pass on to Peter?
Yeah, that's fine. I'll go out and pass over to Peter Meadows.
Okay, so hopefully you can hear me okay, Andy?
Yep, you're coming through loud and clear, Peter.
Okay, so I've just thought for the first part of this session, I'll just expand a bit on the observers challenge that we've set members of the section if they wish to take place this year. If you remember, 3 or 4 years ago, we had a challenge related to polar faculae, but this one we've called Capturing the Dynamic Sun. And I think most observers, myself included, we take an observation each day if we're lucky, work and weather permitting. But how many of us spend time actually comparing, for example, a sunspot group from one day to the next or between observations? And so the challenge really is for all of us to spend a bit more time, perhaps, looking to see how things have changed over time. So in white light, as Lynn showed earlier, the appearance of sunspots can change from day to day. You can have a small spot one day, then the next day you've got a moderately sized group. Things tend to be a bit more dynamic in hydrogen alpha, so certain features can change from day to day, like filaments, but others, like prominences, can change over the space of hours or even minutes. So, as I say, the idea of this challenge is to get a bit of extra information out from our observations. So one thing we can do, so as I mentioned, we can use white light, hydrogen alpha, or indeed calcium K. And one thing with white light, if you tend to have a large sunspot, they can be followed from rotation to rotation. And the question is, well, how do they evolve from rotation to rotation? And that can be quite an interesting project in itself to see how long sunspots can last for. And the very largest ones can last for 4 or 5 rotations, which is quite a long time. So as I mentioned, hydrogen alpha is very good for smaller timescale features like prominence and flares. And one thought I had was, I assume that solar flares can be seen in calcium K, but I don't remember seeing any images or reports of calcium K flares. And if there are some, how do they differ from hydrogen alpha? Because you're looking at a slightly different section of the chromosphere. So if anyone's got any observations of those, that would be very interesting as well. So we thought the challenge would run from May to September this year, which obviously coincides with the summer period for those of us in the Northern Hemisphere. We wanted to have a sort of a time constraint so that people can focus their efforts for those few months. If you want to start earlier, that's fine, or want to continue later on, that's okay as well. But obviously with the longer summer days in the UK and in Europe, if you've got able to observe the sun over, say, a period of 8 or 10 hours, you might see quite a lot of change particularly in hydrogen alpha features. And so that'd be quite a good time period to look at any changes. So I should stress that we're also looking for drawings, and we know that some members make drawings in hydrogen alpha, in fact, as well as white light. And the idea would be to include some of the ones that we receive in the newsletter, and hopefully we can put something in the journal as well, which we did for the polar faculae. So I went back through my own images and drawings from, in fact, they're all from the previous cycle. So the one at the top shows just a drawing that I make using the projection method in white light. And the photographs from the 19th onwards are just using a camera of the projected image in the telescope. So it's not direct, it's just simply photographing what's at the end of the projection box. And that's the group that Lynn showed. So that was the largest sunspot from the previous cycle. And then on the bottom right is the same group again. And I managed to use the PST telescope, a fairly modest telescope, to actually monitor the changes in an X2 flare, as it happens, over the period of 45 minutes or so. And then on the one on the left is of filament, again over the period of, well, in this case, a couple of hours. And you can see changes in the structure of the filament, particularly the central part of the what I assume is an arc, and so that faded over the period of a couple of hours. We've already seen some examples of things changing in Roger's prominence image earlier, and also from Carl as well. So it's that type of thing that we're looking for, and I think it will just enrich what we do already as a section. So if anyone has any questions on that, then obviously you can put them in the chat here, but also don't hesitate to contact Lynn or myself, and we will help you out. We'll probably announce this challenge in sort of April, May time to the whole membership via the newsletter. Okay, so this is the main presentation as I'm doing this afternoon, and it's titled Cycle 25 Development and Expectations. So I'm going to try to do a bit of predicting, and predicting in solar activity is just like comets, is very difficult, but nevertheless, let's see how things might develop over the next 2 or 3 years. So how's this cycle going so far? And the plot there shows the BAA observations. So the blue data points are for each day, and the black curve is the monthly average, the mean daily frequency for each month. So as Lynn mentioned, towards the right-hand side, December and January were particularly high. February so far isn't quite as high, but it's still very good. The most of 2022 was roughly the same, a slight increase, and obviously that was on the back of coming from very low activity in 2020. So you can also see from the daily data, you can see that there are certain days where the activity is particularly high, and others where it's not quite as high, and that's linked up with the certain longitudes of the sun tend to be more active than others over the rotation period of about 28 days. And that shows quite nicely that the same longitude probably is coming back active for 7 months in a row. And we've also seen some quite variability between the northern hemisphere and the southern hemisphere. Some months one hemisphere dominates compared to the other, and then vice versa. So I'm also interested in looking at the size of sunspots, the area of sunspots, and using images from the Solar Dynamics Observatory. I've been measuring the area of particularly the larger sunspots groups that we've had this cycle so far. And so we've had quite a few groups that are sort of around 1,000 millionths of the sun's visible hemisphere. There's been 1 or 2 slightly higher. So 0 degrees is the central meridian of the sun, and minus 80 or 90 is on the eastern side, and then obviously plus is on the western side. And the sunspots will appear on the east and then progress towards the west. And the thing to note is that all the groups of this sort of area have only been since the beginning of last year, May last year. We didn't have any of this sort of size before that. So the most recent large one was in January, active region 3190, which was seen with protected naked eye. And by protected naked eye, I mean that you're using some safety film or eclipse glasses to observe the sun in white light with a naked eye. It's interesting to also note that about 2/3 of the large sunspots groups tend to appear after solar maximum, so we can still expect to see quite a lot of large sunspots in the next few years. And I've put this plot here prepared by John Cook, and it shows again BAA observations. On the left-hand scale in grey, we've got the sunspot number going back to 1990. So this was cycle 24, the most recent complete cycle, and then cycle 23 back in the early 2000s. But it's also superimposed on that is the prominence mean daily frequency, which indicates on the right-hand scale the number of prominences seen on each day. And this is quite interesting in the sense that for cycle 25, we're already higher than in cycle 24, which is quite encouraging for the current cycle. So in other words, there's even now we're seeing more prominence each day than we did for the whole of the previous cycle. So I'm going to show you two prediction models that have been prepared by professional solar scientists. And the first one was prepared back in December 2018 by a panel from NOAA and NASA in the UK, an international panel. And their task was to, based on previous data, to decide how big and when the current cycle is going to be, and when the peak is going to be. So they've come up with they came up with a smooth sunspot number of 115. So the smooth sunspot number is based on the international sunspot number, where it's averaged over roughly a period of 12 months. And the effect of the smoothing is shown on the cycle 23 and 24. So in light blue, you've got the monthly values, and then you've got the running 12-month average shown in sort of a darker blue line. So that essentially are saying that cycle 25 is going to be roughly comparable to cycle 24, with a peak in July 2025. So that's one prediction. And if you entered the Christmas quiz, you'll know about the other prediction from McIntosh et al., which tends to be referred to as the Terminator prediction. And this actually goes back quite a few years. So that they've been working on this for quite a long time. And so back in 2014, they identified a feature on the sun which appeared to play a role in how cycle 23 transitioned into cycle 24. And for that, they were using what's referred to as bright points. So these are in the extreme ultraviolet, and they're small bright regions in the sun, and they used SOHO images, and then more recently solar dynamic observatory images. And they noticed that the number and density of these bright points dropped off to almost zero at the same time as sunspot area at mid-latitudes crossed 1,000 millionths. And they also determined that this transition took place over a very short period of time. And in fact, they say over a time period as short as one solar rotation, which is, in terms of the sun, That's a very short time, a period of time. So they inferred that this transition was a crucial episode in the magnetic field of the sun and how the sun changes from one cycle to the next. So the 22-year magnetic cycle, the Hale cycle. And they also deduced that the overlapping magnetic systems played a role in determining the shape and amplitude of the solar cycle, particularly the next solar cycle. So just to illustrate that a bit better, this is a plot from one of their papers. So the top half shows the sunspot number. So you've got the total sunspot number, both hemispheres on top, and then you've got the north and south here. And then the bottom half, you've got, again, sunspots shown in sort of of different sizes, shown as black diamond shapes. More importantly, they've sort of highlighted the latitude and trend for these bright points, these extreme ultraviolet bright points. So, for example, you've got this pinkish color coming down here, but you can see that it actually tails off after sunspots have disappeared, and in fact it tails off and ends, as I've mentioned before, when there are sunspots on the disk from the new cycle. And these dashed lines are the what they refer to as the terminator. And you can see the same thing in the southern hemisphere. They start off at very high latitudes, 40 odd degrees or even higher, and then progress towards the equator and end much later than you would determine from sunspots alone. So they then, using sunspot data, they extended the when these terminators took place, and so they, as I say, the terminator ended when it was very close to the equator, and it was at the time also coincided with the time of rapid sunspot production. So I said they've managed to determine 14 of these terminators, and they've been able to assess the time period between terminations and the strength of the next sunspot cycle. And this is shown here. So on the vertical axis, we've got the smooth sunspot number, as in the NASA prediction, and then we've got the time between terminators from the previous cycle. So they made a prediction, I think, in around 2020, and at that time, the terminator event from the most recent cycle hadn't occurred. So they were predicting a sunspot number of around 230 or so. But in fact, the terminator event only took place at the end of 2021, and that meant that their prediction for this cycle, cycle 25, is a sunspot number of 184, with a maximum in 2025. So you can see here that this is their prediction. M is the mean for all sunspot cycles going back to 1750, and this one here is the NOAA prediction. So they're indicating a much stronger cycle than NOAA, but of course the proof is in what we actually can observe and what the sunspot number actually is. So I've plotted here the actual data, so the monthly data, sunspot number R shown in green. So these, as I say, December and January were particularly high. And then in light blue is the NOAA prediction, and as you can see, it doesn't fit very well to the actual data. If you move the NOAA data back 6 months, as shown in the purple, it fits the rise of the cycle, the first year or so of the cycle fits quite well. But since then, it's actually deviated quite badly from the actual data shown in green and red. However, if we look at the McIntosh et al. Prediction shown in black, we can see that that has a much better fit to the actual data. It's perhaps a little bit high, but not very much. We're only talking about a sunspot difference of about 5 or so. So that's pretty good. And certainly the monthly data fits quite nicely, especially with the last couple of months of high activity. So because the smooth one is averaged over 12 months, the most recent value that you have is 6 months old. You have to wait 6 months before you get the smooth number, but it's looking encouraging. And if we use the same data and just change the time scale, so go out to 2030, you can see that the NOAA prediction, even with the 6 month offset, we're talking a peak of around 2025. And the McIntosh et al. Prediction, we're talking sometime in 2025. So the timescales are not too different between the two predictions. It's just the scale is quite different. So even if it's in reality the actual data is a bit under the McIntosh prediction, we're going to have a really nice cycle. So how does that compare with previous cycles? So essentially we're showing the same data. Again, in blue, we've got the NASA prediction shifted by 6 months. And then in red, we've got the McIntosh prediction with error bars. And then in green, we've got the mean of the solar cycles in 1750. So what we can see is that certainly if the McIntosh prediction comes true, we're going to have a much better cycle than cycle 24. And it's going to be sort of comparable to cycle 23 in the early 2000s, which is really nice for those of us that remember observing back in the early 2000s. So just to summarize, so as I said, activity has been particularly high in the last couple of months. And then I've shown these two predictions. I should say there are other predictions around, but I've just shown these two. So the NASA prediction seems to be underestimating the strength of the current cycle, whereas the Terminator prediction seems to be, certainly at the moment, seems to be a pretty good fit to the cycle. And if that's true, then, as I mentioned, cycle 25 will be better than 24 and comparable to 23. But as with all things, really, we have to wait and see. And a really good way of doing that is to observe ourselves and submitting observations to the section where we collate them, and we'll see for ourselves how things are progressing each month as we go to a maximum based on both predictions of around 2025, which is only a couple of years away. So that was so if anyone has any questions, I'm happy to answer.
Thank you, Peter. If anyone has questions, then do type them in the Q&A on Zoom or chat, or else if you're watching on YouTube, put them in the comments and we can read them out from there.
So I thought it was quite interesting with the McIntosh prediction that they were saying that the Terminator event occurs when sunspots get up to about 1,000 millionths. And they determined that the most recent Terminator took place at the end of 2021. And it was only in 2022 that we started to see these largish sunspots. So that seems to tie in quite nicely.
Yeah, so good to see activity building up again.
Yes, yeah.
If there aren't any questions at the moment, Lynn, I noticed that on the schedule, it's 3:15 for Roger, but Lynn and Roger, do you want to start shortly? Actually, I do see we've got a question coming in from Michael Nichols. There's a comment on the flares and prominences can be seen in calcium K, but they are not as prominent.
Okay, I've seen prominences in calcium K, but I don't think we've ever seen a flare in calcium K, so that would be interesting. If anyone catches a flare in calcium K and hydrogen alpha at almost the same time, that would be really interesting.
Peter, I'll be showing one shortly.
Oh, great. Okay.
Lynn, would you like to introduce Roger?
I'm happy if you want to break. Either way, I'm fine.
No, I just build that in for some leeway with questions and answers, but as we've not had too many, if you'd like to go ahead, Roger, I mean,
Okay.
we can have that flexibility further down the line, perhaps.
Great, thank you.
Okay, then. We can see the screen, I presume. So.
Yep, seeing your slides in edit mode, then.
Yeah, I'm just going to wait. I can get the pictures to bring it down. There we go. Good.
Yeah,
okay.
Now looking good in presentation mode.
Good. Okay. Well, this talk is, well, the title it basically says it all. So let's get on with it. Firstly, just as a preamble, it's not intended as a detailed tutorial for processing solar images, as it'd be really a bit tedious, I think, in this sort of forum. So I've omitted some of the detailed tweaks I do, but it's rather an outline of the main processes I've found satisfactory and useful for me, largely because they're free, to make best use of this entry-level solar telescope. The main one I've made use of is one to use an image-derived flat frame correction. I don't pretend that this little scope of mine is competitive with some of the exquisite images we've seen today. And elsewhere, after all, you can't get these images out of a small telescope. You can't change the laws of physics, as the Scottish used to say on Star Trek. Well, in particular, I like to record full disk images, and I've gone through many iterations to make best use of the scope and camera. But again, just as another preamble, it's often quite difficult to compare images you see on the web, because they don't tend to indicate their orientation or whether they're reversed or flipped or whatever. So all my finished images are oriented with solar north at the top and east to the left, as are the gong and solar images. Also, the date and time and the equipment information I record on the image itself. I tend to regard simple imaging as a method of recording observations for someone like myself who's artistically challenged rather than imaging in its own right. But there's a big overlap between these two things, of course. For example, I found this drawing on the SBA website, really quite an excellent drawing, I thought. But really, I don't think I could hope to produce something of that quality. But alongside it is one of my images, which is done at the same time as that sketch. A sketch is better than a sketch. So I couldn't really hope to record the amount of detail even on that simple image of mine as a sketch. So whilst I'm not discouraging people from doing it, I'm just saying I don't think I can do that. So that's really what I see as imaging. So the equipment we're talking about here is about as entrance level as you can get. It's the Lunt LS35 THA telescope. It's a 35 millimeter aperture telescope, 400 millimeters focal length. It's got a front mounted full aperture tilt tuned Etalon, and it's got a B400 blocking filter. Now the solar disk size with that focal length is in fact 3.5 millimeters. So it only just encompasses the full disk. It's also got a helical focuser, which irritatingly rotates the eyepiece, but it's not fatal. But it's just one of those things. It is not available anymore, in fact, so Lunt have discontinued that one. but they do have an LS40, which is 40mm one with a B500 blocking filter. I don't know anything about that really, other than I've seen the adverts. It's essentially instantly available. It's indoors, but the downside of that is it's diffraction limited. The instant availability of it, though, did enable me, just to scope this, to acquire images on 213 days in 2022. So you can catch holes in the cloud. So 213 out of 365, I don't think is bad, really. So let's have a few words about diffraction limitation, as it's going to crop up several times. This the Rayleigh limit for separating stars at point objects is usually thought as 1.22 lambda wavelength divided by the objective diameter. If you crunch through all those figures, which I'm not going to tediously go through, you end up about 4.7 arc seconds with a 35mm scope, or about 5, let's say. Now that's if you want to separate 2 point sources, 2 stars or whatever. It's probably more useful for solar images to think of something slightly different, which is the width of a feature, or the full width half maximum of the point spread function, to give it a more technical term. Now that one, this term is 1.03 times the wavelength divided by the scope diameter. And again, crunching through the numbers, you'll end up with that at about 4 arc seconds with a 35mm scope. So what does this actually mean in practice? Well, there's a full image, a full disk image in hydrogen alpha, and there's a magnified version of it underneath it. I took this image again from indoors, from the windowsill, in December last year. And if you look at the striations, the linear sort of features on that image, and calculate what they are, at their thinnest, they're about 4 to 5 arc seconds wide, which is reasonably consistent with the predicted 4 arc second full width half maximum figures. So that's what it means. That's the sort of limitation you get. That's on with the images. The rest of the equipment is, I use a Bressa microcular full HD camera. It's a very low cost camera, 55, 60 pounds. It was still available when I wrote this presentation. Whether it is or not, I don't know. Still, it's 1920 by 1080 resolution. Pixel size is, as it says there. With a 400mm focal length, you end up at about 50 by 28 arc minutes. Given the solar disk size at the prime focus of 3.5mm, and residual vignetting with a 4mm blocking filter, you can see, but you can compensate for that using this flat frame correction I use with this median filter, which I will discuss a bit later. I prefer to image the full solar disk. I like to see the full solar disk. So a 15-minute by 28-minute sensor size can't accommodate a 30-minute solar disk size. So what do? Well, we can use a focal reducer, but my own experience with this gives it less than optimum results. So you can use a Barlow and make a mosaic. By the time 2 Barlow will make the image size effectively 60 minutes. And then if you work all that out, you really need a 6-panel mosaic to cover the whole disk. That's a bit cumbersome to acquire and process on a regular basis. So after a lot of trial and errors, I ended up with a 1.5 times 1.5 Barlow, a homemade one, in fact. This results in a 2-panel mosaic with a reasonable fit and overlap. And that also then translates as well to about, with that camera, to about 1 pixel per arc second. That, given the scope's 5 arc second resolution or so, seems reasonable and comfortably inside the Nyquist sampling limit. So fundamentally, that's what I do. There's the setup with the optional Amaryllis. Sitting on the windowsill, it's not facing exactly due south, but it's facing sort of southwestish. But that's what it all looks like. The software I use is all freeware. I use SharpCap for acquisition, and I usually acquire about a 400 frame AVI and 2 frames exposure, 2 sequences exposure optimized for the surface and 2 for the prominences. In favorable conditions, I use about 90% of the frames. But there's a bit of a health warning here. The microcular produces compressed AVIs. And a 400 frame AVI in its compressed form is about 40 to 60 megabytes in file size when it's compressed. The current release of SharpCap, the current version of SharpCap, decompresses that data and will only save the decompressed data, which turns that 40 to 60 megabytes into 2.4 gigabytes for a 400 frame AVI. I have a discussion with the author of SharpCap about this, and that's the way it is. That without going into detail of it, that's what you get. And the earlier versions of SharpCap, this is version 2.9 instead of the version 4 or whatever it is at the moment, actually saves the compressed data, but it isn't any longer available. But I still got 2.9 in my machine, and that's the one I use. So 2.4 gigabytes file space, 400 frames on 213 days a year is quite a lot. I then use Registack 6 for stacking and the initial wavelet processing, and then GIMP for merging the mosaic panels and for the final processing. In order to compensate for the smaller blocking filter and just construct a mosaic in a reasonable, easily way, you need to correct, obviously, the uneven illumination of the individual images for stitching the mosaic panels together. There are a variety of ways of doing this, but what follows is a simple, pragmatic method I use, using a synthetic image-derived flat frame generated by employing a long median filter. Now, median filters, unlike linear filters, which are Gaussians, median filters tend to suppress very bright or very dark spots, and they limit effects caused by the edge of the disk. You don't get a blurry edge of the disk. Now, that can be contentious when you're filtering data, but all we're using it for here is in generating a synthetic flat frame, which in fact it's ideal. So the raw image that I would start with is that's a surface exposure optimized frame from the 400 frames. It's stacked and it's wavelet processed. So that's the image that I basically start with. And then apply a median filter to that, which gives us that image, which gives us the overall brightness of the image without any of the details on it, but without being distorted by the edge of the disk. What I then do is to set that, duplicate the image layer, median filter it, and in the image layer stack, I set that the field filter one to a divide mode. And the divide, if you've got through the maths anyway, which I'm not going to tediously go through, will basically divide by that flat frame and give you that image. But the scaling of that image obviously isn't very appropriate. So I then apply the curves function from GIMP to that image before doing the divide. And when you do the division, you get that image. Now, it's worth at this point, I think, just comparing with that image with the one we started with, which is there. So that's what we've now got. That's what we've now got. That's what we started with. So you then do that twice for each half of the disk. Stitch the two together. And again, there's various ways of stitching it. I'm not going to go into today. And then adjust the result with, again, the curves parameter again to whatever you like. Now, as an incidental, this process also reduces the effects of limb darkening. And there's an early image I did some years ago with the original image there on the left and the one on the right using this flat frame correction, which obviously takes away the limb darkening. Now, you might not like limb darkening, or you might like limb darkening. Again, it's a bit of a personal choice, I think, but that's basically what I do. So going back to our main image, I got the frames in the of the surface, and I then do another 2 exposure optimized frames for prominences, which is there on the left. And then you can colorize them to whatever you choose. and then merge them together with an appropriate disk mask. And so the final product looks like that. I then take that image and then rotate it so the north is at the top and east to the left. And that now gives us a full disk image and gives us an opportunity out of interest to compare that with the images on GONG. Now the GONG instrument is 28 millimeters in diameter, so it's not that much different to my 35. Let's just take the colorization away and just so we can compare that directly. That's not a particularly good GONG image, in fact, but it's just one I happen to use. So there's my image on the left, and there's the GONG image on the right. Once I've done all that, I then, rather than let all my images get out of hand, I then tend to create a collage of images like this, with the full disk in the middle and with magnified versions of features that I see or like scattered around it. So that's sort of my final product. That's the images that that's the sort of image that I post to Peter, and also on space weather, in fact. So that's my final product to keep them manageable, basically. The 400 millimeter focal length of that hydrogen alpha scope is the same, in fact, as that of my 80 millimeter f5 refractor. So with appropriate filter on that one, it enables me to get a direct comparison between hydrogen alpha and white light, because the images are the same size, basically. So that's the white light image from the same, more or less the same time as the previous hydrogen alpha image. That enables us to play a few tricks with the images. So here's something I occasionally like to do, and do a fade between the hydrogen alpha image and the white light image, which you can imagine that's a journey through the chromosphere to the photosphere if you're particularly fanciful. But there's the hydrogen alpha image fading into the white light image. Now you can catch transients, which Peter was talking about, because of this instant availability business. I mean, here's a flare which goes back to 2021, in fact, that there's 4 over a bit about half an hour, and that is there. These images are from the GONG website. So there's the flare. You can see an image 2, 10 minutes after this first one of the sequence. Now, in this particular case, I didn't catch the whole of this sequence, but I just caught the final bit of it, which is just there. That was my image. That just caught the image as the flare as it was decaying. Now that allows us to go another comparison just to see what the effects of this diffraction limitation are. So up on the top left there is the GONG image. Find a pointer. There we are. That's the GONG image. This is my windowsill image. Now this image I found for the same time on space weather, which was for a 70 millimeter refractor with a Daystar Quark camera in hydrogen alpha filter, in fact. So you can see quite clearly the effects there of the diffraction limitation of my image compared with the bigger ones. Nothing surprising about that, I don't think. That's just a bit of physics there. But that's what the effect of the diffraction limitation is. We'll see a bit more of that in a minute. The other things that you can see are this was a recent flare. These are transient events. This flare occurred over a period of about 50 minutes back in the 5th of February. It was quite a big flare on the eastern side of the disk. Again, I didn't catch a sequence of images, just caught the flare as coincidentally during the imaging, in fact. This one you've already seen, actually, because Lynn showed this, but there's this sudden eruptive prominence. I took the first image of that, and then half an hour later took another image, and lo and behold, there was this huge prominence, and I was a bit startled by that. So I then did carry on to do a sequence of images over a period of about half an hour. And in fact, if you look at the difference between these two images, that one, and in fact between that one and that one, there's less than a minute between those pair of images, those pair and those pair. So you can just see how quick this particular prominence erupted from virtually nothing into fading away there. At the bottom there's an animation of it. That's just that image sequence there, and there it is on the full disk image to give you an idea of its context. So that's a transient that you are caught because of this instant availability I have. This is another one which is these bubble prominences that I've seen before, and I'm not going to dwell too much on this because we in fact discussed this at the last webinar. But these strange prominences we saw around solar minimum, around the north and south poles of the sun. In fact, observing these things and talking to Lynn first inspired me to join the BAA. This one is hardly a transient, but nevertheless, it is something that happens over a shortish period of time. That was the transit of Mercury back in 2019, at least the start of the transit of Mercury against the hydrogen alpha sun. More recently, here's the relatively recent partial eclipse. And again, I think Lynn showed this one briefly, but that's the partial eclipse. Now, this one was quite interesting because by looking at these on space weather, I encountered this image here on the right by well-known Pete Lawrence. And now this was done at more or less the same time, but I then discovered, I didn't know, that Pete only lives a few miles away from my house. So not only are these two images done at more or less the same time, but they're done from more or less the same place, which is interesting. And this also gives us another opportunity to look at this diffraction limitation business. So I just blew up sections of these images. And again, you can see Pete's image with his with more comprehensive scope than mine, and the image from the 35mm scope. So again, you can see the effects of the diffraction limitation on that image. Some more interesting images of recent images, at least. Here was a really very nice and large phylloprom. This one dates back to when's that date? On that June last year. A really rather nice phylloprom there on the northwestern limb. Here was another huge prominence that we had back in this May last year on the southwest limb, and this was all over and done with in no time as well. So there's this large prominence. This is simply a magnified version of that. But that image there is 23. That's about 50 minutes later. So that prominence developed into that over a period of about 50 minutes. There's a relatively recent complex filament that was visible. That one's in September last year. And here's another prominence. Again, this one dates from what was this? Again, August last year. And the sequence here, it was a large prominence and developed from there to there over a couple of days, and then it ended with a bit of a flourish. So on the final day, it did that. So it finished its life with a bit of a flourish over a very short period of time, a 45-minute period, in fact. I can only welcome Peter's challenge, and obviously these events. One of the things that attract me to solar observing is the fact that these things happen in a very quick time. Things change. Here's a particular large and complex spot system fairly recently. That's January this year. And this one is interesting to me because, again, I've got a white light image of this one at the same time. So there's the white light. There's the hydrogen alpha light one. Again, this allows us to play tricks with the fading again. So there's the hydrogen alpha fading into white light again on the full disk this time. So again, it's just a bit of a gimmick, really. There's nothing particularly remarkable about that. It gives you a perspective of the comparison between hydrogen alpha and white light. This one is not really very remarkable, except that it was this morning. So this is this morning's image of the sun at 10:35. So there's a 10-minute gap in the clouds this morning, which I did manage to make use of. And so there's this morning's image done as I've been describing them. The one other thing you've got to be prepared for with this sort of thing is prepare for the unexpected a bit. We're not far from Birmingham Airport, and occasionally that happens. So that's a white light image. I can't remember what sunspot that is, but that feature I don't think is a solar feature. So just to wind up, in conclusion, the small Lunt telescope nicely fits on Indo's windowsill. The images you get are broadly comparable with the ones on the Gong website because the apertures are similar. It's comparable to the 80mm f5 reflector for white light. It's instantly available, but it's diffraction limited. The images I've got here are with a very low-cost camera, HD camera, and you can get 2-frame mosaics and images as you've seen with the 1.5 times Barlow. To do that, I use this image-derived flat frame correction to reduce the vignetting, and the same process works to reduce limb darkening. And just as a postscript to these conclusions, I thought I'd just add this. It's worth remembering that I'm not trying to push back the boundaries of human knowledge. I'm doing all this because it's a hobby, it's fun. So that's basically what I do, and that's what I've ended up doing, and that's the lot. Thank you very much, and if there's any questions, I'll be only too pleased to answer them.
Thank you, Roger. Yes, we've got a few questions coming in. The first one is from Diane, which is actually kind of more of a comment, which is she has a helical focuser on her 35mm hydrogen alpha telescope, and she changed it for a ZWO HF 1.25 helical focuser that can be locked off to stop derotation after focus.
Yes, you can. I work with sort of the fixed focus here, and basically I just slide the camera around, which fits into the eyepiece. So I'm not really bothered about it. But yes, I've got another focuser which I've never bothered to put on this, which doesn't rotate the camera.
Then we have Simon Brown asking, do you get any reflection from the window pane? If so, how do you process this out of the image?
No, fundamentally, the objective is very close to the window. I think there are. If you look carefully at the images, you can see that the background changes a bit, depending how clean the window is, I think. But no, I don't have any trouble with reflections with this. I think the objective has got to be very close to the window for this to happen. I do this with other with not solar images, with deep sky images, and I've got a little 90mm cathodoptric scope, which the mirror, of course, is at the back of the scope. That does produce reflections.
Then we have Kim Hay and Kevin Kell asking, what is your white light equipment, and is there room on your windowsill for both?
There is, in fact, but if you go back to the image of the thing on the windowsill, it's on an equatorial mount with a simple motor drive. Each imaging sequence here takes only 10-20 seconds, so that there's Registax takes care of any image movement and rotation, in fact, in that period of time. But finding dark objects from the window is a bit more contentious. So I've got an Altaz go-to mount, which fits on the windowsill as well. But I don't use that for solar.
And you may have covered this, which is Tony M asking what effects you see from the window glass.
Well, you can see I've done no particular corrections. Having said that, if the sun in this, the usual problem with imaging from indoors that people tell you is if you open the window, you get air currents rushing out, and they will distort the image simply because of the air turbulence. So I have discovered over the last summer in particular that I do get better images with the window open, because it's the internal to external differential temperature is virtually zero, and I don't get any air currents. But during the winter, this morning's image, for example, that was with the window closed.
In which case that may answer in part the next question from Michael Nichols, which is, your images are very good given the small aperture, but would you get even better results if you didn't image through a window? So I guess when the temperature differential isn't there, you do.
That is true. Also, what is warm inside, if it's early in the morning, I might be still in my pajamas. I don't have to go outside, and I'm not bothered by the recent gales. And
then from Peter Meadows, how long does it take you from image capture to final image?
The capturing, each 400 frame AVI takes less than 20 seconds. So it's a couple of minutes to acquire the images. To process them to the final image you see might take me, well, you've seen this morning's image, 10:35. By the time I'd got other errands to do this morning, it took me an hour or two to do that.
Right. And just checking, I think that's the last. I'll just double check on YouTube. Nothing. We've actually got 50 people watching across Zoom and YouTube, not including the presenters. So that's a nice number for today.
Good.
No more. So thank you very much, Roger.
Good. You're welcome.
I think next up we've got Andy Devey on the imaging techniques and making solar movies.
Hello, everybody. I'll just share screen.
Great. Thanks, Andy.
Yep. Okay, can you see my screen? Okay.
Yep, see the first slide, and yeah, hear you fine.
Okay. Welcome to everybody from Southeast Spain. Okay, when it comes to imaging, you always need to start with a specific objective for each imaging session. Now that will depend upon whether you're going to use white light, hydrogen alpha, calcium K, or another. Some people use spectroscopes, and as time goes on, more and more different platforms for observing the sun are becoming available to us amateurs. But I will only concentrate on the first three because that's all I've got available to me and all that I have experience with. And then the other thing is whether you're going to go for a single image, panels for a mosaic, or if you're going to go for a multiple frame through video camera. So the stills can be for single image or parts of a much larger mosaic. And at the moment, my record for a winter solar mosaic, which is 12 frames, but for a lunar mosaic was 80. So that certainly gives you some headaches. And then whether or not you're intending to do a animation run. So there are web assistances that can be used. So I always start with a weather forecast and what I can see outside through my windows and outside in the garden. I always use the Sat24, which you can see the last hour and a half, nearly 2 hours of cloud animations. So particularly if you take a long time to build up because you've got a lot of equipment, then it may show you that by the time you've built up, you could be clouded out. And that happened to me many, many times when I used to live in the UK. Another one to consider is have a look for the jet stream. Obviously, it's something you're not physically going to see, but it could have a major effect on your local atmospheric seeing. I also look at the no prediction on space weather. And when you look at the graph showing flare activity, sometimes you may be able to spot patterns associated with certain sunspots, which I'll come to later, which may help you predict when you have a chance of catching a flare or even a big flare. They also give you the probabilities for M-class and X-class flares as well on the front page of Space Weather. I don't personally contribute, but you can pay to get alerts sent to your mobile phone of flares when they're actually being sent occurring. And then the other one, and it's just been mentioned by the last speaker, but the current images on the Global Oscillation Network group, GONG, and particularly if you go into its animation sequence, you can get not only where the flares are occurring, but it's also very good on filaments and prominences, so you can see where the most dynamic features are that are worth imaging, or particularly if you're going to do animation runs. This graph at the bottom is a 2-week graph from Space Weather, which I've put together showing all the flares associated with AR 2192, which was the biggest sunspot of last cycle. And that gave off 6 X-class flares and over 80 M and C-class flares. So the atmospheric seeing, the wind and ground conditions are the 2 big factors. I'm not going to talk about when you cloud it out because we all know about that. You just don't bother. But with my observatory, if it's really windy, I just don't bother. I don't open up. But what I do is I do daily observations, and if it's particularly windy, I will do them through the window. The altitude of the sun. Here in Spain, 37 degrees north, obviously the sun's higher on the ecliptic's higher. So that the higher you are on the ecliptic plane, the less atmosphere you're having to look through. So when you're looking straight up at the zenith, you're looking in rough figures about 6 miles of atmosphere or 12, 13 kilometers. If you're looking at the sun rising above the sea on the horizon, you're looking through about 120 miles of atmosphere, so a lot more dense. The other one to consider is, as I mentioned earlier, is the jet stream position, because you may have what looks like potentially perfect weather conditions outside, and then when you do a visual observation, the image could be boiling away at the edges, and that could be a direct effect of the jet stream above you. And I always use the seeing to decide on what focal length I will select. So with my white light telescope, I use a TOA 130 Takahashi, and I'll image between 500 millimeters, which I'll use for a full disc, and that's using a 50% Barlow reducer, which I screw straight into the nose of my camera, or I can go two times Barlows and take it up to 4,000 millimeters in white light. And then similar for hydrogen alpha, I've got a 90 millimeter Coronado hydrogen alpha telescope, and for a full disc, I will put the 50% reducer in. Excuse me. So I'm imaging at 400 millimeter focal length, or I can push it right out to 3,200 millimeters. Now, the further out that you push the focal length, the amount of light into your camera is reduced. So the speed at which your image capturing increases. So whereas you can probably capture it more than 1,000th of a second at short focal length, when I go to long focal lengths, I may be imaging at between 1/60th of a second or a 90th of a second, in that range, which causes atmospheric seeing to increase. This is just a photograph of my small portable. I've got a Coronado PST calcium K, which is parallel to a hydrogen alpha Coronado PST, and that's sat on top of a 80mm Williams Optics telescope with a BAA filter on the front of it. BAA filter paper, the optical one. And when you're doing visual, always follow all the safety steps. Now, that particular kit, I've got a little suitcase box, and that goes on holiday with me. So when you take something like that into a hotel, you can guarantee you're going to get to know everybody in the hotel, because everybody likes to have a look. And on a night, you can take the solar filter off and show them different, either planetary or lunar objects, etc. The main instrument I use for imaging is, I've got it fitted on a steel pier that's full of concrete. And this photograph is from quite a number of years ago, 2014, I believe. So the mount has changed from EQ6. I've now got an EQ8, which is still loaded to full capacity, but it's a much more stable structure. On that mount, I have got, that's the Takahashi 2A130 with a Lunt solar wedge. This is a Coronado 90mm hydrogen alpha with a second echelon on top, double stacking it. And in front of the wedge there, that's the DMK 51 camera. And this I've got parallel at the side of it is a 90mm Coronado calcium K. They were quite rare, and these are old technology. Telescopes were manufactured between 2007 and I believe this was 2008 or 2009. Now, my observatory is like a wooden cube. So I lift the floor plate out and it runs on rails. And you see rails, and it's fastened to the floor with these turnbuckles. Now, what that gave me the ability to is open up, and from leaving the house to opening up and imaging, I can do it in less than 5 minutes. So I'm not building anything up. The only thing I need to do to start imaging is I always have to refit my blocking filters. They are particularly sensitive to a poor atmosphere. So they come out and I keep them in a plastic box inside the observatory with a desiccant to keep moisture away. Otherwise, I wouldn't have had the longevity of and the luxury of using these telescopes as long as I've been able to do. So, image capture, the options available are DSLR, which doing that, particularly when you've got monochrome such as hydrogen alpha or calcium K light coming in, you're only going to be using 25% of your pixels. So I quickly discounted DSLR. So I always use a video camera. I've got two options of DMK, which is the 21 and the much larger 51 chip. Generally, I use the 51, but it's got a frame limit of only 12 frames per second. If you're lucky, normally I might get between 1 and 2 per second. So I tend to restrict my imaging runs to only 200 frames, two reasons. One, I'm approaching a minute mark, so solar features can kind of change by the time I have grabbed my image sequence. And the other factor is that with 200 frames, I'm generating video files of nearly 2 gigabytes, which gives you an enormous amount of volume of data generated. So for image processing, I always start with AutoStackit. The 3 is available, but I'll be honest with you, I'm still using 2. I then put the final images into Registack 6 and use wavelets for that. For my processing, putting the mosaics together, and also for doing the animation sequences, I use Photoshop CS5. The only other thing I do while I'm imaging, my first images, always the data for a flat field to get rid of any dust donuts and other artifacts from the telescope. So it's been mentioned earlier, but very, very important to use correct image orientation, and I use the same as Gong, and also on the space weather from the Solar Dynamic Observatory, with north to the top and the sun's east limb to the left. Put the date, universal time. I do an estimation of the seeing conditions, and also I have capture data. What I tend to do is I have a little notebook in the observatory with me, and I jot the information down. So I'm showing you this picture for 2 reasons. One, to show the physical size of some of the features that we can get on the sun. And another one, which is a beautiful system for measuring them, which was produced by a Frenchman called Guy Berry, who I had quite a lot of email correspondence with over 10 years ago. And Guy was kind enough to produce this English version. The Guy's a Frenchman, and it's La Règle Solar, the French version. But on it, you've got the scale for which you can use for the heights of prominences. You set it onto your limb, so because this image is in the photosphere, sorry, the chromosphere, I've set it, when I could get my pointer, so that it fits just inside the where the top of the photosphere is. You've got a scale to measure features across the diameter of the sun, and these are in hundreds of thousands of kilometers. You've got the Earth's disk, Jupiter's disk. You've got a scale of, so they can measure features along the circumference, but also this nice Earth-Moon distance scale. Now, the reason why I've selected this particular feature is because this filament, which was on the 9th of February 2015, and this is one of my 12-panel mosaics, the feature was about 1 million kilometers in length. So as you can see, it's going from plus almost 300 kilometers, sorry, 300,000 kilometers, through 0 to over minus 700,000 that side. So one enormous feature. And the original image that I've produced here, if you look at it on the computer, is about 1 meter in diameter, so fairly high resolution. And I was imaging at 1600 millimeter focal length with my Hadron Alpha telescope on that. So when we come to actual animations, this is what I fell in love with and really drew me into solar imaging, which I started in about 2006, 2007, and is actually the reason why we moved to Spain. But here you see a white light image filmed on 22nd of June last year, active region 3038. What you're seeing here are 34 minutes in variable seeing conditions, but with white light, you can get a nice effect of the boiling in the convection cells. If you look carefully, you can see, and I don't know how well this image is running for you via Zoom and over the internet, but you can also see some dark mottled areas, which is it's oops, sorry about that, which is a heat feature. But also, when you look at the penumbra area, these fibrils that run in, you can physically see them running in. Now, if you're able to image consistently for an hour or more, you can see them running in much better as they slowly slide into the umbral region. Now, we've been mentioning white light flares earlier. I personally have not captured a white light flare, but one of the sunspots, this was AR 2192. It was the largest sunspot of cycle 24. I believe it was over 2,700 millionths in area, and this was on the 19th of October. So it's just started to, a couple of days as it's starting to come around from the eastern limb. But you can see the complexity of it. It was an enormous, and during its transit, which was from the 15th to, I believe, the 29th of October, I was pulling 18-hour shifts. I was worn out by this sunspot. Every available minute I was capturing data, then through the evenings I was image processing and animating. So this is one of my 12 panel calcium mosaics of it. So again, this image is about 1 meter in diameter. You can see the size of the sunspot compared to some of the more smaller normal size sunspots. So this area was bigger than the planet Jupiter. So from that same imaging run, this is a calcium K animation, and you can see some of the flaring activities. These were only C-class flares, but you can see a pair of flares there. There's flaring there, and there's also some small flaring across this light bridge here that runs in across the umbra. So flaring is much better to see in hydrogen alpha. So same area, and Peter showed a sequence of images that he got from the same region of this exact same flare. Now, I saw it from 1421 to 1536 universal time, so I caught it through its peak, and as you can see, the area of flaring extends way beyond where the actual sunspots themselves were, and I estimated to be about 1.5 times the Jupiter's diameter across this diagonal area. Obviously, you're getting some shortening because you're starting to look down the edge of the limb. Now, this one here is the biggest flare I've captured through the current sunspot cycle. And in this very large area here, you will see an M5.4 class flare, which is going off there. Now, this one was over four-hour imaging run. This 4 hours 23 minutes, that one. And the thing that limits me with my imaging run is often meridian flit. So the longest imaging session I've done on a continuous run before meridian flit was a 7-hour imaging session. So the biggest flare I've personally captured was the second largest flare from cycle 24, and that was a X 8.2 class. I believe the biggest one on the same day, it was a 9.3, and that was from the 10th of September 2017, and it was associated with AR 2673, average grade 3 seeing conditions on that one. But as flares develop, the features that they produce changes. So when you get a better option to see flare activity changes when they are closer to the solar limb. So in this one, you see the flare break, but then the post-flare loops start to lift and develop afterwards as the magnetic field starts to restructure itself. But also, when you look at the solar limb, as well as seeing larger features, you can see the spicules jumping up and down as well along the limb. So, best post-flare loop system sequence I ever captured is this one, and it was from 19th of July 2012. And I captured this with my Coronado PST. And I was using a 2-time Barlow, so I actually pushed the PST to 80mm focal length. But as you can see, I was imaging there for over about 2 hours, just under 2 hours. And this is a 120 frame sequence, so sorry, 110 frame sequence. So I was imaging every minute there to capture that. And that followed an M7.7 class flare on the limb. So I'm just giving you a comparison here where I've pushed the 90mm telescope to the maximum at 3.2 meter focal length. And I've overexposed the chromosphere, so you can see the magnetic loops and the plasma running down. And what's interesting is this plasma, it runs down each side simultaneously. So it's not doing a loop, it's running down from the center as the plasma precipitates from the corona, sticks onto these magnetic field lines, instantly cools, and then starts running down them back into the chromosphere. This is an image sequence I'm showing you of a prominence. It's not one of my best sequences because the seeing wasn't very good, but it's the only time I've ever captured a dark plume rising from the chromosphere. So as you can see, it seems to have its own self-contained magnetic field, which disturbs the prominence as it lifts up. I'm showing you a couple of images here, and these are flares that are caught a couple of months apart. And solar flares, when they break, they can create all sorts of interesting and strange phenomenon. This one on the right that I'm showing you, you get an ejection of material that then falls back and precipitates back here. So that one was not quite a coronal mass ejection. This one here generates a shock wave in this area, which you can see. My computer's freezing a little bit, so at the moment. Another thing is, when you're imaging, it's always worth disconnecting from the internet, because you never know when you've got a Windows update feeding data to you in the background, and that can severely affect the speed of your imaging camera. So if you disconnect from the internet, that will help you get the best camera feed available. So this next one is, I can do full disc images and animations, and I'm at 400mm focal length here with the 90mm telescope, which gives fairly nice detail both on the surface and also the prominences around the edge. Now, what's happening on this one? If I can just get my mouse to work again. There we are. After the flare, there's a shock wave runs in an arc underneath that filament in northwest direction. You can see it's a much lighter as it runs across. I'll just let it run a couple more times because that one seems to be sticking a little bit on my laptop. So, hopefully these are all running smoothly on my computer, but with the data transfer via the Zoom link and internet, there's going to be quite a lot of loss in quality, what you're seeing, and also possibly in its velocity. Here I'm showing you a pair of M-class flares, and the one on the left, post-flare loops and plasma loops are being ejected vertically, and that's a bigger one. That's I think 6.7 class flare, that one. This one here is a 3.7. But what I find really interesting in this one, you can actually see the loop fail, which when it breaks, it actually, you can see the flare actually in creation at that time, and very, very faintly above that one, there are post-flare loops visible. There we are. You can see them there and there. So that flare actually blasts underneath those loops as if they're acting like a tunnel. So it's only what's visible. And then this is an M2 class flare I've caught from this cycle, which was, I believe it was the 18th of August, but I can't see because of the Zoom data at the top of my screen. But that one blasts out, and actually you can see plasma coming straight out. So you've got a CME actually in action there, coming out and on its way earthbound, that one. Now, I particularly like CMEs because they are the largest solar structures that we can capture. And the further away from the sun, the bigger they get. So the biggest one I've ever captured leaving the sun was back in April 2010. And at that time, I'd not even started doing image animations. I just happened to be lucky enough to take 5 images of it. And they're all same period of time apart. And that's during a 37-minute period. And the height of that thing when it's leaving is Earth to Moon distance and twice as long in its length. Now, with my personal solar telescope, PST, which is also a 40mm introduction instrument, this is quite a large prominence eruption which formed as a CME, and I did image another sequence further out than that where I took the BAA out, but I've not presented that in this one. But again, a nice capture with a PST, which is introductory, very similar in comparison with the 35mm HA telescope, which was just been presented in by the previous speaker. And this is one that I've actually rotated so it's lifting vertically. But that was a big one from the 11th September 2013. And that's a sequence that runs from 8:07 to 9:23. So about an hour and 15 minutes, 16 minutes duration, it's gone. And the biggest one I've captured to date, and this one was a 3.5 hour sequence that lifted off on 4th of September 2012. So I've not gone into any great detail today, because what I would suggest to anybody that's interested seriously in solar observing, join Solar Chat. There's lots of fantastic images in there, some real top amateurs, the very top amateurs. And last year, well, a couple of years ago, a group of them, headed by Christian Aldrich, they put together solar astronomy book, which was released last year in English language version. And I was fortunate enough to review it for the BAA last year, but I cannot recommend it highly enough. So before you buy anything, have a look at what other people are doing, because reinventing wheels takes a long time and can cost you a hell of a lot of money. So somebody somewhere will have done it, and I find that, particularly on Solar Chat, people really do want to help you, and things that maybe seem like insurmountable problems to you, somebody's found a way, whether it's a software issue, a problem with your telescope, or a processing issue, or just sheer guidance. These people will help you. And that, thank you to that for your attention.
Thank you, Andy. Those are really fabulous videos. I must admit, I'm also jealous of your location, but those, so in those videos, yeah, even with the smaller telescopes, were really incredible.
Well, I thought it were important to show a comparison between larger and smaller, because I've been fortunate enough to own both. But even with a small instrument, you can get some beautiful images from the sun.
Are you still doing B&B, Andy?
Yes.
Ah, there you go. If you fancy a few days in Spain with some tuition on movie making, Andy's your guy.
And you can use it all.
Yes, and Lynn's just pointed out as well that Solar Chat is sponsored by the BAA. So we've got
Stephen, who runs it, fantastic guy.
Yeah, I've seen a lot of his stuff on Facebook, and he's always very busy.
Yes.
We have a comment from Simon Brown, which was that the space weather live alerts to your mobile phone or tablet for the solar events is free when you sign up on the website, and the alerts come within a few minutes of the flare commencing. That was a good call, Simon. Any other questions? Nothing coming in on YouTube. Well, I think probably everyone's just a bit wowed by the images, so all the videos. So thank you again, Andy.
Okay, the only goal I've not achieved from coming to Spain, and that's not my fault, it's the sun. I want to catch a super flare above X10.
Yes, do you think that might have, do you think any chance that a few days later that might have some kind of impact on the Earth?
Oh, very possibly, yes.
So get it processed quickly.
Yeah, the super flares are classed as anything above X10, and there were none in cycle 24. So the biggest was that, I believe, that 9.3 in September 17. So quite close, but not a super flare. So
fingers crossed for this cycle.
Oh yes.
And from Michael Nichols, he wants an X10 and above. I would be happy just to get an X. Yes, I've done a little bit of solar observing, but I've never seen a flare myself. So yes, I'd be grateful for anything. Thank you very much, Andy. Next up, we've got Paul and Paul Hearn and Andrew Thomas. I'm not quite sure if this is a kind of combined talk or if Paul is going first.
Yes.
Yeah, so Paul is going to speak on geomagnetism and cosmic radiation.
Yeah, thank you so much for inviting us. It's been just fascinating this afternoon. Really enjoyed it now anyway. Yeah, we've made a very slight change to the running order. I'm going to be talking about cosmic radiation detection by muon counting. And then my colleague Andrew Thomas is going to talk about geomagnetism and sudden ionospheric disturbance. He's more of an expert in those areas than I am. Right. Oh, I've got to share my screen, haven't I? Can you see that?
Yep, that's all coming through well.
Oh, good. Okay, perfect. This afternoon, then, we're going to do just a little bit of astrophysics so that we're all up to speed. And I'm sure that as far as solar physics is concerned, that you are way ahead of me on that one. And in fact, I'm hoping that you can answer some questions that I have a bit later on. I'm going to look a little bit about the instrumentation, and then I've got a few observations and then a slide at the end just to conclude. Right, I've got this obligatory slide here of the relevant Nobel Prize winner, and this was Carl Anderson in 1936, and I've included this for two reasons. One, because we're talking about muon counting this afternoon. Secondly, he was a lecturer in physics at MIT, and this links with our story a little later on. So where does cosmic radiation originate? Well, from outside the solar system, supernova, massive energetic events. I'm not going to explore this afternoon. We're going to, in fact, look at what's more relevant to us, and that's from the sun, cosmic radiation from the sun. And I'm sure that you have seen this slide before, but I make no excuse of showing it again because I just love it. So we've got a mass ejection here pointing straight at planet Earth, and it shows the distortion in the magnetic field, which Andrew will explore in his discussion in a few moments. And we've got the galactic cosmic rays, as they're noted here, being accelerated towards the planet. And these cosmic radiation are high energy particles, predominantly protons, nuclei of hydrogen and a little helium, X-rays and gamma radiation, all squirting at us. And this is particularly interesting, as many of us in the radio astronomy section observe other solar phenomena and opens up avenues of correlation. And we just love data, playing with data and looking for correlations. And there's plenty of scope for that with solar observations with using radio astronomy. Now muons, as we're going to home in on now, are thought to be generated with a mean energy of 6 GeV, maybe a little bit less, but they are massively energetic particles, and they're formed at an altitude of around 15 kilometers, but I guess that's a bit variable. Right, a little bit of astrophysics, not a lot. I mentioned earlier, the cosmic radiation impinges the upper atmosphere, and predominantly protons interact with the nuclei of the atoms in the upper atmosphere, producing a whole range of subatomic particles. We've got p ions, k ions, neutrinos, of which there's quite a lot in literature and television documentaries, but also from our perspective, muons. And these shower down and can be detected at sea level. So there's one interesting thing about muons. And I mention this because it is included in the A-level physics syllabus, and that again is relevant to something I want to mention a little later on. But it's a great demonstration of time dilation. Now, a muon will move at the speed of light. And if you're a physicist, it's 99.999%, which I guess is significant. So every 660 meters outside its frame reference will appear only as 3 meters in length within its own time reference, which means it has time to travel from its point of origin to be detected. And this takes just 1.5 microseconds, which is a good thing because the half-life of a muon is only 2.2 microseconds. So it gives us time to detect the muon and to count it. And the muon will then go on to decay into an electron and different types of neutrinos and other stuff that happens in the realm of quantum physics, which is beyond me and the discussion this afternoon. Right, I've included this because it's particularly relevant to us. So the top data set is over a 20-year period is the sunspot number, the daily sunspot number. And we can see here we've got nearly three cycles. We've then got the neutron the neutron flux, which again correlates very nicely with the sunspot count, inversely correlated there. And we've also got on the third data set the X-ray data from the GEOS satellite. And I will just mention that NASA are very generous with their raw data availability. And we can pick this up and do as we choose with it. And in this 30-year span we've got here, a 20-year span we've got here, we can see that there is a correlation with sunspot activity. And then we've got the cosmic radiation, predominantly protons, and again we can see here that the daily mean count does correlate with sunspot activity. And then I've included here the magnetometer data because Andrew's going to pick this up in a minute, but we can see here that there's an annual change in the geomagnetic contribution, but not so much of a correlation with the sunspot activity. Okay, now this is something that I've only been looking at in the last few days, and if there's anybody that's come across this phenomena, this effect in the solar section, I'd be very interested to have some discussion with you either offline or in the questions later. So we can, this is an effect where there's a decrease in the observed galactic cosmic ray intensity following a CME. And it's due to the magnetic field of the plasma solar wind sweeping some of the cosmic radiation away from the Earth. And as one would expect, the magnitude would be related to the size of the CME, the strength of the magnetic fields within the CME, and the proximity to Earth. Nothing too surprising there. And here we've got another data set. At the top, we've got the, this is just for a few days, sorry, few days in March 2012. And we can see on the 7th, there was an event, and the, let me see if I've got my laser. I've got a laser pointer, but it's just taken me back a slide, bear with me. Yes, so the second data set, we've got the cosmic radiation, and here it's from GEOS, and they've got a proton spectrometer, I suspect, because we've got 6 different energy bands here. But you can see there's an increase here from the effect from the event that's under discussion. And then on this data set, we've got a reduction, and we're looking at some neutrons here, and the a few days into the event, we can see the neutron count decreasing due to the Frobush effect. We've got also at the bottom data set is the magnetic measurements, and we can see that there was some massive change on day one of the event, and again on about day 3. Moving on, there's a bit of background noise I can hear. I don't know if you can. I do apologise. There's a birthday party in the house this afternoon. Okay, so muon detector will detect background radiation as well. It detects beta, gamma, and muon. But we're only interested, of course, in the muon contribution because we're interested in the cosmology. And so how do we get rid of the background radiation? We stack the detector. And I took this image just last week, and it just happens that the lower detector at the moment of the exposure is recording an event, not a muon event, because a muon event would occur simultaneously on both detectors. So we've got a bit of beta or gamma from the geology, from the building materials, whatever. So yeah, as I said, an event registered with both detectors simultaneously will be a muon and not just local background. So moving swiftly on, the instrumentation. So there are many different technologies, but commonly used these days because of its enhanced sensitivity and decreased cost, and the cheap processing power of single board computers and semiconductors. The scintillator with a photomultiplier bonded to it optically is the technology that we've used in the main, and what I'm describing here. So the scintillator is 25 cubic centimeters in volume, and then there's a photomultiplier bonded onto the onto it, which is just a 6 millimeter square, and that's what it looks like outside of its case. The whole detector element is bound up with PVC tape to keep the light out. So observations. This is the muon count from July to December, and we can see that as the going from on the x-axis we've got the month and day, and then on the y-axis we've got the time of day, and we can see that in the towards the middle of the day there's a higher count rate, and as the day length decreases we have a reduced count rate. And as I mentioned earlier, we have the opportunity of correlating muon data with other data sets, and we're at a very early stage of looking at the data and correlating with all the other myriad of data sets that are available to us. And Mark Prescott has put this together for us, and he is looking at solar wind velocity with muon count, and I don't think this particular data set tells us very much on that score. Here we've got the muon counts again over that 6-month period, but correlating with the neutron data and again the solar bolt wind speed. I'm not going to try to draw conclusions from this just at the moment. We're at certainly I am at an early stage in trying to understand this and get my head around it, as are others. But if you want to invite us back in a couple of years' time, I'm sure we'll have a lot more data as opposed to the other stuff I've spoken about earlier this afternoon. Okay, conclusions, right. It's a great project for undergraduate teaching, and we already have a number of universities using the detector that I described earlier, the scintillator photomultiplier combination. What I didn't mention was that this came about because a physics teacher at MIT, hence the reference back to Carl Anderson, was frustrated that his physics students were very keen to model stuff on the computer, but not so keen on getting their hands dirty, building stuff, getting it working, debugging, writing code, and doing some real measurements and drawing conclusions, which is what undergraduate physics should be about, in his view, and I tend to concur. And so the muon detector that I've described is open source design and one that's used at MIT for teaching astrophysics for the physics. Okay. It's a great project for academic and amateur collaboration, and we're already seeing this because the muon detector technology is becoming increasingly inexpensive. Certainly, it's within the realms of undergraduate teaching labs to purchase. They're available as kits or as built units, and there's so much real science that can be done with very little. If you love data processing, then again, it's something good to get your head around for developing those skills. Future developments will include detection correlation with space weather, climate, lightning, etc., neutron flux, as I've shown earlier. Detector energy calibration and muon and energy spectroscopy. Now, this is a bit of a long shot, but I think it might be within the bounds of a very inexpensive detector. And I know, and I'm in communication with the prophet, Bristol University, who's got one of her dear undergraduate students on the case. And then with client-server technologies for data presentation for multiple detectors. If we can imagine thousands of detectors across the globe, each uploading an individual pixel to an image, then we can imagine a muon telescope with an aperture the size of the planet. And on that score, I'm going to hand over to Andrew. If I can find the stop share button. Thank you.
Yeah, my screen. Okay. Well, I'm not quite sure how to follow that, or the imaging that I've seen presented this afternoon, except to say the gentleman who presented how to do your imaging with lower cost equipment, well, the great thing about what I do is it is absolutely at the bottom end of the lowest cost equipment, and an awful lot of it is DIY. So what I became interested in was first discovering that radio astronomy was a thing for amateurs, and secondly, discovering that you can do it in a very, very simple way. It's a great platform for learning a bit of data processing and electronics on, which is what I've been doing for the last few years. And you can collect some real data that somebody is interested in correlating and writes up regularly for the BAA journal. John Cook has been a stalwart of this and does a wonderful job every month of collating people's results. So all I can do is, is speak about what I do, which is to look at the effects of the sun on the Earth's ionosphere and the Earth's magnetic field. And I have some instruments I use. And what I'm going to focus on is not so much the instruments or the physics, but simply the results you can get very easily in your own shed. Now, those who have a shed in a sunny clime, I envy you. I don't like the cold nights, I don't like the clouds, and I don't like the rain. So radio astronomy struck me as a good deal. What we see, the Earth has an ionosphere of charged particles at various heights. And I was a radio engineer in my career, but my counterparts in the 1920s would have been a lot more familiar than we are now with the action of the ionosphere. The only people relying on it now are amateurs. And very, very low frequency, very long wavelength transmissions used by governments to talk to their submarines. And it's those transmissions that we use to look at the effects of solar flares on the ionosphere. Just bear in mind that the frequencies we're talking about here are the top end of kilohertz, which if they were sound, younger people would be able to hear them. And they have wavelengths of sort of tens of kilometers. So it's not, it's quite a different area of radio to what we're used to for things like mobile phones and Wi-Fi. So I run a number of instruments, a couple of receivers for different sorts of VLF, a magnetometer, and I also use my computer sound card to monitor various VLF transmissions. It just gives me a few more options. And it all lives in a rather sort of damp looking shed in not very sunny Kent. Now what we see for this is a graph I took in 2017, and it's almost the first actual result I ever obtained, which is why I still use it. I'm quite pleased with it. The effect on the ionosphere is from X-rays, and this is a trace of the GEOS satellite, which, as Paul said, is freely available from NASA. This is the received signal, and the station which transmits from Germany. It is quite handy because it turns itself off every morning. Whether this is for tea break, it seems to be some sort of station identification that if it proves you're tuned into the right frequency. And as the sun rises and the ionosphere forms, the received signal stabilizes, and there's an X-ray flare, and here's the effect we're measuring. Now, John Cook, we submit results to John. The time of the start, the time of the peak, the end time, and there is a table for working out what they call the importance of these events. Now, this is the sort of data I'm taking now. This was end of April last year, and here I'm monitoring 1, 2, 3, 4 different radio frequencies, and we're now nicely first part of I started just before solar minimum, so this is all new to me. And what we're seeing is one M-class flare, a just X-class flare, and other things happening around in C-class flares. So we're seeing almost constant disturbance of the ionosphere, and the different radio channels and their different path lengths and the difference in the phase between the sky wave and the ground wave causes some channels to increase, some to decrease. This mustard coloured trace and the green trace are two British transmitters near Anthorn on the Solway Firth, and Skelton, which I think is just sort of south of the Lake District. And from where I live, they're exactly anti-phase. So one goes up and one goes down. This one, it actually passes through a sort of null point. So it starts going up and goes down. The physics of this is quite interesting, and there are 1 or 2 observers who do some really nice calculation work about what this is saying about the height of the ionosphere. But for a very simple forte in looking at the effects of the sun on the earth. This mostly is DIY and a quite a nice kit. The bane of everything in the radio domain is interference. The reason my receivers got banished to the shed was we had solar panels installed. And here we see the sun coming up on a nice sunny day, the solar panels switching on, and at the other end of the day they switch off. And all this fuzziness and noise is from the solar panels. So I moved out somewhere a bit quieter, which is it's only a couple of, maybe only about 100 feet, but it's far enough just to get away from the interference on the roof. Now, some of you may already have dabbled with a magnetometer, and there are various designs of magnetometer available. People talk about 2-axis magnetometers, where you measure the field pointing north, the field pointing north, the field pointing east-west, and the field pointing straight down. I have a 2-axis magnetometer which measures the angle of the field between due north and the angle of the field between horizontal. And as we move further towards the pole, that angle increases to the point where at the pole it's vertical, and at the equator it's horizontal. You don't make a real measurement of the intensity of the magnetic field. You make a measurement of the changes in the magnetic field. And here from two years ago from this solar cycle, a nicely disturbed magnetic field on the 3rd of November 2021. And what I'm going to do on the next slide is show how this goes from just starting a disturbance just after midnight on the 3rd through this very disturbed period into the next day. And I use this to see how what I'm recording in Kent, how that compares with what the British Geological Survey is recording on their science grade magnetometers, which are in, they operate 3, one in Devon, one in Esdalemuir near South Glasgow, and one up in Orkney. And the effects, that looks quite dramatic, but in Orkney, the effects can be much, much greater as you get nearer the poles, where all the charged particles are channeled and the auroras start to occur. So here we see, these are my results at the bottom. And I took two different graphs and just literally pasted them together for a slide very quickly for a presentation one evening. And you can see how the disturbances here tail off and the next day is quite quiet. And when comparing that, particularly with the yellow trace on the British Geological Survey, they nicely correlate. I think I'm getting valid measurements, and my project for the future is to work out how to present these and how to characterize the disturbance in the magnetic field. I don't think I'm going to see the aurora, unfortunately, in Kent, but I think the effects of the sun, charged particles, and the other things that happen on the magnetic field is one of the more interesting things, and there are some nice correlations with the radio signals as well. So that's what I do, and I think that's just another facet. Some people might say this is geophysics, but I think it falls nicely into astronomy, where all these measurements usually started. Happy to take questions, both for Paul and myself, and thank you very much for indulging our hobby.
Thank you, Paul and Andrew. Fascinating to see or hear about other sides of solar observing. And
there are a lot of other things that can be done on this as well, but trying to pack it all into 15 minutes is very difficult.
yes, it's always a challenge to make for a succinct presentation, whilst including all the important bits. And we have a couple of questions from earlier on, which was towards the end of Paul's talk, from Martin Kinder.
Yeah, I can take those.
He was asking, how fast do gamma rays travel in comparison with muon? And would a vertical traversing gamma ray trigger a hit, or would it be too slow to be captured in the trigger window?
Yeah, great questions. There's a follow-up question as well. I'll take them both together. X-rays and gamma rays are not directly observed at sea level on Earth, which is probably a good thing. They're absorbed within the atmosphere. So we need not concern ourselves too much with that. How fast they travel, electromagnetic radiation, so to all intent and purposes, very close to the speed of light, I would imagine. Now, others will probably have a better handle on that than I. The second question, I just had a look at the data on this. A muon will deposit 2 to 3 MeV of its energy in our scintillator, and you may recall that I said they had several GeV of energy. So basically, the amount of energy they lose being detected in #1 detector does not impact their ability to be detected in #2 detector. When we do the coincidence in software, we're looking at something like a 30 microsecond window. So if an event occurs within, 2 events occur within 30 microseconds, then it's a muon. There will be a probability that random events can occur in that time frame, but it's so small that we need not bother with it. I use electronics to do the coincidence, and it's significantly faster than 30 microseconds. So I think that does answer the...
Can I pick up the bit about gamma rays?
Yeah.
Paul, can I pick up the bit about gamma rays?
Please do, yes, yes, yes.
I'll share my screen again. That one. Okay, I hope you can see another graph. On the 9th of October 2022, it was significant enough event to actually make the news media. The most powerful, brightest gamma ray burst ever observed went off. And I'd noticed a notch just there in my BLF traces. And when I looked at the GEOS data, no significant activity from the sun. So I scratched my head and thought, well, okay, I'll have a look at that tomorrow. That's a bit odd. By the following morning, the news about the gamma ray burst was well and truly out there in the press. And that gamma ray burst was first off powerful enough to ionize the D layer of the Earth's ionosphere, which there's always been some speculation as to whether a gamma ray burst would be bright enough to affect the ionosphere. So first off, now we know the answer. Yes, it is. It's strong enough to affect the affect the ionosphere, even though it's daylight and it's getting a normal dose of solar X-rays to energize it. The question about do gamma ray bursts reach ground level? The answer we've nicely proved from that burst was no. I would be intrigued to know how close and how powerful a gamma ray burst would have to be to put gamma rays on the ground, and I don't think it would do anything alive much good if it did. So fortunately, our atmosphere is very good at shielding us from gamma rays, and we kind of proved it.
Yes, that's very good and a relief. And I was also interested to hear about the cosmic ray detector, because that's actually something very similar to what I did 30 years ago in my undergraduate. I didn't build it, but used sort of a similar setup, but with sort of paddles about sort of 0.5 meter or 12 inches to a side, set up in the physics labs to detect cosmic rays and look for coincidence between two paddles as they travelled through.
We had a talk where a group was doing. Some people may have seen this on the television. Muon tomography of structures like the Great Pyramid to detect hidden chambers. That's done with very large scintillator blocks and 10,000–20,000 pound photomultipliers. We managed to get in considerably lower cost than that. But the interesting thing about your description of the big paddles is that that's what they're using for that kind of surveying. And the group, I think it's Sheffield, is being commissioned by Network Rail to survey for voids above tunnels using that technology. And they've done a demonstration to prove that they can detect voids above tunnels, and they're developing it into a practical surveying technique to go and often do other railway tunnels, because the problem is if you get voids developing, the danger is that they will collapse the tunnel.
Yep, very important.
So practical applications of astronomy.
Indeed, very good. And I think, Lynn, were you wanting to do a general Q&A at the end?
Yes, please, especially as we have a little bit of time. So I think all the panelists can reappear and be available for any questions from anybody.
Yes, I think looks like we've got everyone just about back on.
Yep.
So again, please, type in the Q&A or the chat on Zoom or the on YouTube in the comments. And so we've got from Kim Hay and Kevin Hall to Andrew wanting to know what the kit is behind you. So I guess that's probably
which one?
But actually, yeah, I should probably ask. I presume you mean? Sorry, to me. Yeah, that's a Skywatch. Just a trying to remember the name of it now. But yeah, this is that's actually what I use for my solar observing. So I've got a little Williams optics telescope and a with a space star filter, which I use when the sun's a bit higher. I do have a problem in the winter months where it's a bit too low and disappears behind the houses, even at midday if it happens to be clear. So it's not quite the time of year where I can see anything yet, but hopefully not too long now.
Is the Skywatcher Solar Quest solar tracking mount, isn't it?
Yes, well, I've actually got the one which is the more general purpose one, which you can use at night time as well. Because I thought if I can get one, then it's kind of, because I've got the William optics, I can potentially use it at night. But yes, it's almost identical to the one which is the solar tracker as well.
Yeah, they're very good because they will find the sun. They're very useful for use in outreach or in schools, something like that. Doesn't require any setup. You just switch it on, plonk it down, and it finds the sun. It's amazing.
That's excellent. And I've also got a Herschel wedge to go with it as well, which gives a nice white light view. And then we've got from Nick Spencer. He thoroughly enjoyed the whole afternoon of interesting presentations and discussions, and really good balance of topics, and thanks to everyone involved. And from Kim Hay and Kevin Kell. For Andrew Thomas, which Raspberry Pi SuperSID code do you use?
Okay, there's a leading question. I've used all sorts of things over the last 4 or 5 years. I've used Radio SkyPipe as a logging program running on a PC. The code on the Raspberry Pi, which I've since replaced the Raspberry Pi with a BeagleBone, because you can get BeagleBones and you can't get Raspberry Pis at the moment, is homebrew, something I've written myself in Python, which simply reads in data once a second, squirrels it away to a file, and every day it starts a new file. So there's 24-hour logging files. On a indoor PC, I then have again, it's home written Python. It grabs the current data file. I'll share this if anyone would like to see it. It grabs the current data file, processes some graphs, and displays them on the uploads them to a website and displays them on the internet. It also will do some data archiving, writing things to hard disk, and what is most important, and I guess you guys must appreciate exactly the same need, which is to back up your data. Your data doesn't exist till it's in 3 places, 3 different places, preferably one cloud-based.
Yes, indeed, wise words. And a comment from Michael O'Connell, which is many thanks to all the presenters and organisers for a great afternoon. Great to have these sessions live online. Not seeing any more questions at the moment.
Okay, in that case, I'll close the session. And I'd just like to give my sincere thanks to all our speakers today, which I think have been absolutely exceptional. I've been fascinated as a non-imager myself. It was absolutely fabulous. So I think for all the images out there, it must be even more intriguing. But thank you very much to Paul and to Andrew Thomas too for another aspect of solar observing. And a big thank you to Andrew Wilson, of course, for hosting this and providing all the technical backup. I'm very, very grateful to you. And also to David Arditti, not only for giving the opening address, but to staying throughout the webinar and supporting it, David. Thank you so much. It was very, very good of you.
Oh, well,
appreciate it.
Excellent talks, as you said, and amazing variety.
And thank you. And a final thanks to everybody out there that's attended. I think we've had about 50 odd at our peak, didn't we, Andrew?
Yeah, no, we had 50 split across Zoom and YouTube, getting up to about 20 on YouTube at one point.
Oh, that's brilliant.
And we'll also have people watch the recordings afterwards. We always get people sort of coming back to see it in the near term, as well as over the coming months. And if there's time, we do have a question from Michael Nichols.
Oh, yes, we have time.
Which was on the 21st of June 2015, he imaged 2 white areas in a sunspot in white light, but no flare was going off at the time. What could they be?
Probably umbral dots. If they were between the sort of on the penumbra border, is that where they would be? Suspecting it would be, and in that case, it's a kind of transparency that you're seeing the hotter layers from deeper down in the sun coming through. That's what these white specks usually are, umbral dots. But if you're seeing it elsewhere than around that penumbra border, then yeah, white light flare possibly, or if it wasn't, then a mystery yet to be resolved.
Well, good question, Mike. I learned something new there. Great. Well, thanks everyone for attending. I'll just close things up on Zoom and YouTube, which will just take me a few minutes. And so thanks to everyone who came and to all the presenters.
Thank you very much.
Bye-bye.
Thank you.
Bye.
Bye.
Bye, everyone. Thank you.